Welcome to week 2 of Bio 6612. So in today's lecture, we're going to cover likelihood functions, maximum likelihood estimation, and we're going to look at a couple MLE or maximum likelihood estimation examples using the Bernoulli distribution. First, I'm going to talk about joint probability density functions. So let y1 through yn be independent random variables that follow the same exponential family distribution. So the density of any single observation, I'm going to denote f of, oops, I don't need to highlight that there, f of yi given theta. And so if you have independent variables, two independent variables, then the joint density is just the density of the first variable multiplied by the density of the second variable. So you can see that here. This is the joint density of F1 and F2 if they follow the same distribution and they're independent. The joint density of those two is written out right there, and you get that by multiplying the two densities. Following that, the joint density of n variables that are independent and have the same distribution is obtained by just multiplying out each of the individual densities for those variables. And the way that we write this, this joint density is f of y1 given ny2 ... yn given theta, and this can be expressed as the product of each of those individual densities. And for those of you who need a refresher, that capital pi I equals 1 to n is the product sign, meaning multiply out all of these values. It's written here. So the joint PDF, which we saw in the last slide, characterizes the probability distribution of multiple y values. Here we're looking at the likelihood function. Well, actually, the likelihood is algebraically the same as the joint PDF, but there's a change in notation that reflects the shift in emphasis from the random variables y with fixed theta to the emphasizing instead the parameters theta, assuming y is fixed. And we use the likelihood function because it's a way to assess plausible parameter values given the observed data. And when I say it's algebraically the same, what I mean is this actually is the same as what we wrote for the joint PDF in the next slide. And for independent, identically distributed variables, you can write that out as the product from I equals 1 to n of any of the PDFs for any individual variable given theta. And then the notation change is reflected here, where now we're emphasizing theta and assuming y's are fixed, and that would be sort of your assumption after you've observed your data, you've collected your data. So we know y now, and we want to know the most plausible parameter values theta given the data that you have collected, y. So here I've actually written out the likelihood for n normal variables. So say you have n variables that each are identically distributed with a normal distribution with mean mu and variance sigma squared. For any single one of those y variables, the distribution, the PDF looks like this. This is the normal PDF for something with mean mu and variance sigma squared. Then to get the likelihood, you just multiply each of those together for each of the n values. And one thing that's kind of nice about this product sign is you can distribute it into the exponential. So if you have e to the a times e to the b, e being exponential, that is equivalent to e to the a plus b. So bringing that down here, this product is moved to this n here, for this constant in front of the exponential. That is not indexed by I, so you can just raise that to the power of n because that's the number of times you're multiplying it together. And then for the exponential here, what you would have is the product over each of these e to the, I'm going to say function of yi terms, just to encapsulate this whole term here. And using this rule that I just talked about over here, we can distribute that summation inside the exponential to say that is equivalent to the sum of each of those functions of yi. And so that's what's happening here. That's how this summation got distributed. This product got distributed as a summation inside the exponential. And it can just be easier to work with the distribution, the likelihood in this form, which is why we do that. So for the rest of the slides, we'll be talking about maximum likelihood estimation. So I showed you the likelihood function in the last slide. And in maximum likelihood estimation, you want to take that function and you want to find the value of the parameter theta that maximizes the function, means gives you the actual highest value of that likelihood. So the likelihood L theta given a set of y, you actually plug in y values that you observe, and you can plug in any value for theta, and that gives you a number, some scalar value. And the goal of maximum likelihood estimation is to find the value of your parameters theta that give you the largest possible number for this function here. Another way of saying that is for a given model, maximum likelihood identifies the parameter values which make the realized data most likely. And as I said before, theta can be scalar or a vector, depending on what parametric distribution from the exponential family you're using. So theta hat, that this little caret on top of theta is called a hat, represents a specific value of theta that you've actually estimated in some way. Without the hat, that's just sort of, it can take on any particular value, then it's still a random variable, just FYI. And so the goal of MLE estimation, or maximum likelihood estimation, is to find the value theta hat, which gives you the largest possible value of the likelihood function. And as you will see, it's often easier to maximize the log likelihood function rather than the likelihood function. And maximizing the log likelihood function will give you the same theta value as just maximizing the likelihood function directly. So in practice, what we often do is maximize the log likelihood instead. So there are three main steps of maximum likelihood estimation. And these steps are written below. In step one, you find the log likelihood, L theta given y, and write this out. And then in the second step, you take this log likelihood and you take the derivative and set it equal to 0. And if you remember from calculus, the derivative of a function at 0 is where you find the minima and maxima of that function. And in the case of the log likelihood, the first derivative of the log likelihood is called the score function, or functions. So you'll have one score function if theta is scalar, and you'll have multiple if theta is a vector. So you'll have a score function for each of the different components of theta. And then in the third step, you verify that this is actually a maximum and not a minimum. So as I said, when you take the first derivative and set it equal to 0, you can find minima and maxima of that function. You want to make sure you're looking at a maximum and not a minimum. And you can verify that by taking the second derivative of the log likelihood at the value theta equals theta hat, the value of the MLE that you found in the previous step. And you make sure that that is less than 0, which means that this is actually a maximum and not a minimum. So let's talk a little bit more about that score function. So the score function, also called the score equation or score equations, if you have theta that has multiple components, is denoted the partial derivative of the log likelihood of theta with respect to theta. If theta has multiple components, meaning theta equals some vector of theta 1, theta 2, etc. up to theta p, if you have p parameters. So if you have a multi-component theta like that, then the first score equation would be, the score for theta 1 would be the partial derivative of the log likelihood of theta with respect to theta 1. And then you would have the second one is u of theta 2 equals the partial derivative of the log likelihood of theta, that is atrocious handwriting, I'm sorry, with respect to theta 2 and so on up to theta p. But for most of the examples I'm going to show you over the next couple days, we're just going to be working with theta where there's just theta as a scalar. And generally you solve for the MLE by setting that score equation, u of theta equal to 0, and then solving for theta. Another common function with regard to MLEs is called the information function. And this will be used a lot in the next lecture to help calculate the variance of MLEs and their confidence intervals. So the information is the variance of the score function, and it's denoted I of theta. So the information of theta is equivalent to the variance of the score of theta, which is equivalent to the negative expectation of the second partial derivative of the log likelihood. So I want to give you a little bit of intuition behind MLEs before we go ahead and calculate a few ourselves. So take some function here. This is an example of a log likelihood function. And this is just a normal distribution here. So the log likelihood function can take any of these values depending on what value of theta you provide that function. So it takes a value of about 0.05 when theta equals 0, again 0.05 when theta equals 4, and it's at its maximum when theta is equal to 2. So the maximum value of that function occurs when theta is equal to 2. And so in order to find that numerically, we take the derivative of that function. And the derivative of this function, when the derivative is equal to 0, that's going to be right where this maximum occurs. So at the value theta equals 2. And to the right here, I've actually plotted the log of that likelihood function. And you can see that the maximum of the log likelihood occurs at the same value of theta. So that's why it's okay for us to use the log likelihood instead of the likelihood when we're maximizing this function. So I'm going to calculate the MLE using a Bernoulli example. In this case, you have random variables yi, and we have a population. So we're going to have y1 to yn. Each yi can take on the value either of 0 or 1. And the probability of y equals 1 is denoted pi. And that represents the probability that some event occurs. It can be like a disease, a genetic trait, or something like that. So for each individual in our sample, yi equals 1 indicates an event occurs for the ith subject, and yi equals 0 indicates that an event does not occur for that subject. So let's go ahead and calculate the MLE of the Bernoulli distribution for data that is in this example. So we start off with the Bernoulli probability mass function. So for discrete values, we have probability mass functions. For continuous values, we have probability distribution functions. And so the probability mass function for a Bernoulli random variable is like this. So the first thing that we do is we want to write down the likelihood of that function. So write that as likelihood, and so the parameter comes first when you're writing out the likelihood. So it's likelihood of theta given y1 all the way up to yn is equal to the product from I equals 1 to n of the PMF of yi given pi, which is then equal to the product from I equals 1 to n, which I'll just denote product I to make it easier, time of pi to the yi times 1 minus pi to 1 minus yi. And that is equal to, you can bring the product into the exponent as a summation, because theta times theta to the a times theta to the b equals theta to the a plus b. That's just a rule of exponents. So you can bring that summation I equals 1 to n of yi times 1 minus pi to the summation of 1 minus yi. And you can distribute that summation to here, to the 1 and to the yi, which gives you equals pi to the summation of yi times 1 minus pi to the n minus summation I of yi, if you distribute that sum up there, that sum. Okay, so that is the likelihood function for a Bernoulli random variable, or n Bernoulli random variables. And so we're gonna use the log likelihood. So if we take the log of that, we get, so I write L, sometimes I write L of, and L as in lowercase to denote that we're looking at the log likelihood. So that's L of theta, that's equal to log capital L of the likelihood. And so that we get that by taking the log of what we just calculated, and what we get is the sum of I of yi times the log of pi plus n minus the sum of yi times the log of 1 minus pi. So we already calculated the log likelihood, and we have that as L of pi equals the sum of yi times log pi plus n minus the sum yi times log 1 minus pi. And so now what we want to do is to take the MLE. So the first thing that we're going to do is take the first derivative with respect to pi of the log likelihood, and that is the score function, which we call the score u of pi. Yeah, so and the first derivative of that is going to be the derivative of the first term, which is sum of yi over pi plus the derivative of the second term, which is that n minus the sum yi over 1 minus pi. Cool. And by setting that equal to 0 and solving for pi, that will give us the MLE. Actually, this was supposed to be a minus here. Solving for 0, we get some yi over pi equals n minus yi over 1 minus pi, which gives you pi equals the sum of yi over n, so the sample mean, which we like to call y bar. So we might also want to check to make sure that this is a maximum and not just a minimum. And we do that by taking the second derivative, which we'll say is here d squared L of pi over d pi squared. That's the second derivative of the log likelihood with respect to pi. That's equal to the derivative of what we calculated up there. And again, we're going to do each of these terms. We can distribute that to each of these two terms here. And what you get is, that's like the derivative of negative sum over pi times pi inverse, so you get negative sum over yi of pi squared minus n minus some yi over 1 minus pi squared. So we want to check that this quantity at the value theta pi equals pi hat, or the MLE, at the value of the MLE, is less than 0. So, well, here pi hat is the MLE, which is equal to y bar, or the sum of yi over n. And we say evaluated at pi equals pi hat. So now we just plug in this value of yi over n into what we calculated for the second derivative here, and that gives us negative yi over n squared minus n minus some yi over 1 minus some yi over n squared, which simplifies out to negative n squared times 1 over some yi plus 1 over n minus some yi. Is this quantity always less than 0? So we know that some yi is between 0 and n. So, and yes, it checks out. So anytime this quantity is greater than 0 or less than n, this value will always be negative. So we know that the MLE we found is a maximum and not a minimum. Okay, great. So I want to quickly walk you through a second Bernoulli example here. Let's say we have 10 randomly selected individuals, 3 of whom have a disease. So we want to find the MLE for pi, which is the proportion in the population who have the disease. And again, here I've written out the likelihood of pi given y, and then the log likelihood, which we calculated in the previous couple slides. So in this table, we have a couple of different possible pi values in the left-hand column, and the value, and then we have likelihood values given those pi values and log likelihood values given those pi values. And as you can see, the pi value that corresponds to 0.3, which is the number of ones over, which corresponds to the MLE, is the one that also has the highest value for the likelihood and the log likelihood. And finally, there's just some R code here. So the plot on this figure is the likelihood for Bernoulli random variables in this scenario. And you can see that that likelihood peaks right around pi equals 0.3, which is 3 out of 10, the MLE in this particular example, and the left-hand side, so it shows you the code for actually generating that plot. All right, thank you. In the next lecture, we'll talk more about MLEs and some of the properties that they have.